Salt solubility. Some of salt are soluble in water. Example, sodium chloride. That is completely soluble in water. But many of salt are insoluble or slightly soluble in water. Solubility of salt we can define as the amount of solid that dissolves in a known value of a saturated solution. Unit for the solubility can be gram per liter or mole per liter. Solubility, normally we can using a symbol is S. Okay, mass of solute in gram dissolved in 1 liter of a saturated solution. Unit is gram per liter. Molar solubility we can define as a mole of solute dissolved in 1 liter of a saturated solution. Unit is a mole per liter. And the next term in a topic of salt solubility is a solubility product, KSP. KSP is the product of the molar concentration of the constituent ion, each raised to the power of its stoichiometric coefficient in the equilibrium equation. For the further explanation, we look at the example 1. Write the ion product KSP expression for each of the following. Question: A. Silver carbonate. B. Barium fluoride. C. Copper 2 sulfide. D. Iron 3 hydroxide. So now we will discuss together. Okay, A. For question number A, silver carbonate. Okay, first we write the molecular formula for the silver carbonate, Ag2CO3. Okay, that is a decomposed by partially or slightly soluble in water to form its ion Ag2CO3 or silver carbonate or argentum carbonate. Okay, dissociate partially to form 2Ag plus CO3 2 minus. So we must balance the equation according to their stoichiometry. Next, we write the KSP solubility product equal to Ag plus to the power of 2 times CO3 to minus to the power of 1. That we call a KSP. Okay, next, barium fluoride. Molecular formula for the barium fluoride is BaF2. So, the next step, we write the equation. Okay, for dissociation equation for the barium fluoride, that is a slightly soluble also. So, BaF2 slightly soluble. Okay, to form Ba2 plus aqueous plus 2F minus aqueous. So make sure, okay, the equation must be balanced. Right. So we write the expression for the KSP. KSP equal to concentration of Ba2 plus times F minus to the power of 2. C. Copper 2 sulfide. I hope from the example A and B, all of you can write the balance equation for this sort, and next all of you can write the expression for the KSP, copper 2 sulfide. So we write the molecular formula for the copper 2 sulfide, CuS, solid, okay, produce Cu2 plus aqueous plus S2 minus. Make sure the equation must be the reversible reaction. The phase must be right. So KSP equal to Cu2 plus time S2 minus. The next question, D, ion 3 hydroxide. So the molecular formula for ion 3 oxide, FeOH3, okay, produce Fe3 plus 3OH minus. Okay, check the equation must be balanced. KSP equal to Fe3 plus time OH minus to the power of 3. Okay, depend on your stoichiometry equation. For the next example, okay, write the solubility equilibrium equation that are described by the following KSP expression. Example, KSP equal to Ag plus time Cl minus. So we can write the equilibrium equation. AgCl solid decompose slightly soluble to form Ag plus aqueous plus Cl minus aqueous. Okay, so we look at the next example. A. Okay, given KSP. KSP equal to, for number A, KSP equal to Ag plus to the power of 2 time SO4 2 minus. For question number B, KSP equal to nickel 2 plus to the power of 3 time PO4 3 minus to the power of 2. Okay, now we discuss together. A. Given the term for the KSP, KSP equal to Ag plus to the power of 2 time SO4 2 minus. So we write the equilibrium equation. Argentine sulfide solid produce 2 Ag plus aqueous plus SO4 2 minus. Make sure the equation must be balanced. B. KSP equal to nickel 2 plus to the power of 3 time VO4 3 minus to the power of 2. Right, so write the equilibrium equation. Ni3 VO4 2 solid produce 3 nickel 2 plus aqueous plus 2 PO4 3 minus aqueous. Relationship between KSP and solubility. The higher the KSP, the greater the solubility, and the higher the temperature, the greater the KSP. Example, MgCO3 solid produce Mg2 plus CO3 2 minus aqueous. KSP given 3.5 times 10 power of negative 8. And PbSO4 solid slightly soluble to form Pb2 plus aqueous plus SO4 2 minus aqueous, whereas KSP is given 1.6 times 10 power of negative 8. So we compare the value of KSP. So we found that the value of KSP for the MgCO3 is higher than PbSO4. So MgCO3 is a more soluble than PbSO4. Where the presence of the common ion will decrease the solubility of a slightly soluble ionic compound. So the equilibrium will shift from right to the left. Solid will be produced. The next example, we add addition of Na2CrO4 solid, that is a soluble salt, to a saturated solution of PbCrO4. The first step, we write the equilibrium equation for the slightly soluble salt PbCrO4. There is a decomposed slightly soluble to form Pb2 plus aqueous plus CrO4 2 minus aqueous. So we write the expression KSP equal to Pb2 plus times CrO4 2 minus, where is given the KSP is equal to 2.3 times 10 to the power of negative 13. So we add a sodium dichromate Na2CrO4. So that means concentration of CrO4 2 minus ion will increase. The presence of common ion will decrease the solubility. So the equilibrium will shift from right. So the effect of the addition of the common ions. First, concentration of CrO4 2 minus ion increase. Second, position of equilibrium will shift from right to the left. Some of CrO4 2 minus ion will combine with Pb2 plus ion to form solid PbCrO4. So the solubility of PbCrO4 will decrease.